Now that you've had some practice writing out some of the simpler shorthand orbital notations, we're going to take today to just look at different ways we can kind of condense this information in a form that's still fairly easy to represent. But we need to make sure that with whatever representation we choose, we are still able to count the important things. That would be our energy levels, our subshells, our orbitals, and even things like unpaired or valence electrons. So the first thing that we can look at in this orbital notation, which is the one that we ended with during the last video, is the total number of electrons we have. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 31, 32. Since there are 32 electrons drawn, we know that this is element 32, assuming it's neutral, that would be germanium. We could have just looked at the last room that was being filled and said, oh, well, there's 2 electrons in 4p. We could have found 4p on the periodic table, and we could have said, oh, well, 2 electrons in, that's germanium. You really can use your periodic table as kind of the model to figure out where you're at if you don't want to count all of the electrons. Now, the first thing that I can do to this orbital notation to just make it simpler to draw is write something called an electron configuration. So this first one is our orbital notation. The second one we're going to talk about is known as the electron configuration. And I just always remember orbital notation, that's an AL there. That reminds me that we're using arrows and lines for orbital notation. Whereas in an electron configuration, we're going to be using just exponents. So basically, the electron configuration would look more like this, where I replace the number of arrows that I drew in each subshell or each room with an exponent or superscript up top to tell me how many total electrons were in that subshell. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, plus another 10 will be 30, 32. There's a total of 32 if I add up all of those superscripts or exponents, and there were 32 arrows. Each little number up here represents the number of arrows, and that's called an electron configuration. Now from an electron configuration, we can still absolutely determine what the biggest energy level is. So we would say 4 is the biggest number. That's 4 energy levels. And we can still absolutely count the subshells or the rooms, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. What it doesn't necessarily let us do as well is count the orbitals because we no longer have the lines. You might be thinking, well, I would just divide each of these in half, which works for most of them. But remember, the 4p actually had 2 orbitals occupied, so we couldn't divide that last one in half. You'd actually have to consider how many sets of bunk beds have at least one person in. Now, this is definitely shorter than this. It doesn't require all those arrows to be drawn, but it's still a lot of subshells to write out. So the other thing we can do to either one of those representations is what you're going to have some practice working on today. And it's called a shorthand orbital notation or a shorthand electron configuration. And what both of these things do is they allow us to condense any of our core electrons, the inner electrons, basically the electrons that are not on the floor of the periodic table where we are. So all of these electrons would be considered core electrons because they're on floors above the floor that we're currently filling in. So that's the 1s, 2s, 2p, 3s, and 3p. All of those electrons are allowed to be condensed down and represented by a noble gas, something from group 18 that has less electrons than the element that we are representing. So since we were representing germanium, we would go up the floor and all the way to the right to find our noble gas, and that would be number 18, argon. So we can then just write the symbol of the noble gas in square brackets like this, we write its atomic number underneath it, and then we can start with the next electron. So argon represents the first 18. We would then find number 19 on the periodic table and say, oh, well, that's in 4s. And then we would just fill in our 4s, 3d, and 4p like we did before. We would still stop with 2 electrons in the 4p because we still only need 32 total electrons. So the first 18 electrons are represented by the symbol of argon. 19 and 20 were in 4s. 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30 were in 3d. And 31 and 32 were in 4p, just like they were on the periodic table. And we are allowed to use this shorthand, or sometimes it's called the noble gas configuration, with the electron configurations as well. So we can start with argon, and then say their number 19 and 20 are in 4s. 21 through 30 are in 3d, and 31 and 32 are in 4p. These shorthands are definitely a lot easier than writing out over 100 electrons. They save us some time, but we do need to make sure that we can still count things like energy levels, subshells, and orbitals. So for our germanium example here, we can still definitely count out the energy levels, because the way the shorthands are written, it's always going to be the final floor that you're filling in. And so you always know that the biggest number is still going to be written out. You can also just think of it as on the periodic table, if I'm here, which floor am I on, or which period am I on? Since I'm on the 4th period or the 4th floor, that means I have 4 energy levels. Subshells are a little trickier because now we're only writing out the subshells for the floor we're on. And we also need to figure out how many subshells were being hidden in argon. And the easiest way to do that is to actually look on the periodic table and count the rooms. So if I want to get to 4p, but I need to start at 1s, how many rooms or how many regions do I pass through? That's 1, 2, 3, 4, 5, 6, 7, and we're in the 8th room. So because we're in the 8th room on the periodic table, there are 8 subshells. They're not all drawn, only the last 3 were, but they're all still occupied. So to count the subshells, we count them on the periodic table. Orbitals are the lines, and in at least our shorthand orbital notation, we still do draw out some of the lines. So that's 1, 2, 3, 4, 5, 6, 7, 8 lines that are drawn out that are occupied. Remember, he's not occupied, so he doesn't count. But all 32 electrons aren't in these 8 rooms. So, I'm sorry, these 8 sets of bunk beds. We also need to consider the sets of bunk beds that would be hidden in argon. So in order to figure out the orbitals, we really just do a quick calculation. We take the noble gas divided by 2 plus any lines you drew. Noble gas divided by 2 plus any lines you drew, which really it should be the atomic number of the noble gas divided by 2 plus any lines that you drew that have at least 1 arrow above them, but then it doesn't rhyme. So noble gas divided by 2 plus any lines you drew. 18 divided by 2 would give us 9 lines that are hidden, and then we just add in the lines that we drew that have at least 1 arrow. So that's 9, 10, 11, 12, 13, 14, 15, 16, 17 total orbitals. We're going to do one more example together. Now that we know the shorthand version, we're going to pick an example from further down on the periodic table so that you can see where these flower rooms come in, because it is really weird. The example that we're going to do together now, let's go with something like tungsten. So tungsten, that's W, has 74 arrows, 74 electrons. In order to draw out the shorthand orbital notation, we're going to go up a level and all the way to the right. Or we could just think of it as which noble gas, that's group 18 member, has less electrons than 74. That would be xenon. So we would start by writing xenon, and then we would put the atomic number of xenon, that's 54, underneath our square brackets. And that takes care of the first 54 electrons. We don't have to draw those now. So then we look on our periodic table and say, okay, well, if that's 54, where are 55 and 56 at? 55 and 56 are here in 6s. So the next room we draw is 6s. Since it's an S, it has one line. There's number 55 and 56. Then we say, okay, well, where's number 57 at? 57 is here in this 5D. So we go ahead and draw out the dungeon. Dungeons always have 5 lines. And that's our 5D room. But this is where something really weird happens. And to be honest with you, it's not the only place that weird things happen, but it is one of 2 examples that you're responsible for actually knowing. And that's because it's actually shown right on the periodic table. If you look closely, 57 is right here. So I would put that in the 5 dungeon. But 58 is not in this dungeon. 58 is down here in the flower room. So after I put a single arrow in there, I then have to draw in the 7 lines that would be in the 4F. And that's where element 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, and 71 are all in. Then 72 goes back to the 5D. Another up arrow, 73, and finally 74. So in the end, I have 1, 2, 3, 4 arrows in the 5D, but in order to fill in from arrow 1 to arrow 2, I also had to fill in all these arrows in the 4F. It looks weird, but the periodic table does tell us that that is the order that the subshells fill in. Because the 5D and the 4F subshell are so close in energy, weird things happen there when we actually look at the emission spectra. So you are required to know that the 4F gets filled in between 57 and 72, and similarly the 5F would get filled in between 89 and 104. Now that I have this drawn out, let's practice counting those other things we need to know. So energy levels are always the biggest principal quantum number. The biggest number I wrote was a 6, so there are 6 energy levels that are occupied. Subshells are always the number of rooms that are filled. And to count that, we look at our periodic table, and we say to get to 74, how many total rooms have at least 1 arrow in them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, but we also needed to fill some into here, so that's 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have a total of 14 rooms that have people in them, so that's 14 subshells. And finally, orbitals. We take our noble gas and we divide it by 2, so that's a total of 27. And then we add in any lines that have at least 1 arrow. 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. So that's 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. We don't count this one because it's not occupied. And then if we want to just do a quick count to make sure that the number of arrows is right, we can do that one of 2 ways. We can start with 54 and then just add these in. So 54, 56, 57, 58, 59, 60, 62, 64, 66, 68, 70, 72, 74. That's 74. Or we can look at the room that is currently being filled and say it's the 1, 2, 3, 4th element over. 5D, that's the 1, 2, 3, 4th element over. So that would be tungsten. You're going to get to do several more examples where you start with a noble gas, something in group 18, and then just fill in from there. And you can do that in both the orbital notation with arrows and lines, or just a preview, we can also look at that using the electron configuration that you'll read more about later. 6s2, 5d, 1, 2, 3, 4, and 2, 4, 6, 8, 10, 12, 14, 14 in the 4f. So this would be our shorthand orbital notation, and this would be our shorthand electron configuration that we'll learn a little bit more about later. Let me know if you guys are stuck or if you need another example to be gone through together.